So the number of protons in the nucleus is what defines an element. Here we have an illustration of a helium atom. In the helium nucleus are 2 protons. Any atom that has 2 protons is helium, and all helium atoms have 2 protons. Over here is carbon. We can tell it's carbon because it's got 6 protons. The number of protons is called the atomic number, and it's given the symbol Z. Z for atomic number. That makes a whole bunch of sense, right? But it comes from the German word Zahl, meaning number, so there is a historical reason behind that. On the periodic table, we have all of the elements listed and all of their atomic numbers are listed. So if we look at this blown up version or blown up square for beryllium, there's the chemical symbol and the integer above it is the atomic number. So beryllium atoms contain 4 protons. Each element has its own name, of course, and its own unique chemical symbol. I made you memorize a bunch of those already. Each chemical symbol is either 1 or 2 letters, and if there's the first letter is always capitalized, the second letter, if there is one, is never capitalized. Many of the symbols are the first 1 or 2 letters of the element's name, like He for helium or C for carbon. Some of them don't seem to make as much sense, like how do they get Na for sodium? The word sodium doesn't have N or A in it. And that's because the symbol there comes from the Latin name for sodium, which is natrium. So it's the first 2 letters of the Latin name. So that's why some of them do not appear to make sense. It also gets a little confusing with things like manganese and magnesium, because they both start with Ma. And so then we go with the first letter and the third letter, and that's why it's Mn and Mg. So all of the atoms in a given element have the same number of protons, but the number of neutrons can be a little bit different. So if we have atoms with the same number of protons, but they have different numbers of neutrons, those are called isotopes. The example here is neon. All neon atoms contain 10 protons, but some of them have 10 neutrons, some have 11, and some have 12 neutrons. So there are 3 different isotopes for neon, because the mass depends mostly on those 2 massive particles, relatively speaking, the proton and the neutron. If the number of neutrons is different, then the mass will be slightly different. So if there are 3 isotopes of neon, does that mean that the 1/3 of all neon atoms are one isotope and the other? No. The distribution appears to be random. Some of them are split almost 50-50 and fairly equally, and some of them there's hardly any of one and a whole bunch of another. Yes?
Is that something you have to be aware of when you do an experiment?
That's a good question. Do you need to be aware of that when you do an experiment? There are situations where you need to know which isotope you're dealing with and you care about that. Most of the time we do not, because we're dealing with gazillions of atoms, and so we just are concerned about the average mass. Yeah, good question. So the relative amounts of each isotope have been studied, and you can look that up. And we find that the relative amounts are the relative amounts are relatively constant. That's a great sentence. Roughly constant. Yeah, let's use a different word. So if you got a sample of neon, bought it from Boston Scientific or some other supplier, or you isolated it from air or wherever, the relative amounts of isotopes would be very close to the same. They're not exact, but they're close enough that most of the time we do not care. And those are usually expressed as percentages. So we'll say, well, it's 51% this isotope and 49% that isotope, or whatever. Those are called the natural abundance of the isotopes. So we've got the atomic number, and we also have the mass number. The mass number is the sum of neutrons and protons. Those are the massive particles. The electrons are so small that we can just ignore them most of the time. The letters for these numbers can be a little confusing, right? So the atomic number is Z and the mass number is A. I would do it the other way around, but they didn't ask me. And I'm not going to be picky or try to trick you about, do you remember it as A or Z? But the atomic number is Z and A is not the atomic number, it's the other one. So it's the number of protons and neutrons in the nucleus. And so we have a couple of different ways of indicating which isotope are we looking at. This is called a nuclear symbol. We use the element, the chemical symbol for the element here, and then we have stacked superscript, subscript on the left side. So on top we put the mass number, and on the bottom is the atomic number. So the three isotopes of neon would look like this. They all have the same mass number and the same atomic symbol because they're all neon, right? What's different is the mass number. I remember having a hard time remembering, does the big number go on top or does the big number go on the bottom? And then I realized that, well, we're often asked, well, how many neutrons does that have? And to do that, you have to subtract the atomic number from the mass number. And look, it's all convenient there. 20 minus 10 is 10. There's 10 neutrons in that one. And over here, 22 minus 10, oh, this one has 12. So that helps me remember. It's stacked up so that I could subtract and find the number of neutrons. Those nuclear symbols are a pain to put into the computer with the superscript business. And so there are other ways that are easier to write to indicate the isotope. And these involve just using the chemical symbol or the name followed by the mass number. Because if we say neon 20 or Ne20 and we need to know the number of protons, we don't need the symbol here to tell us. We have a periodic table. So you can assume that a chemist or someone studying chemistry always has access to a periodic table. So we don't actually need that subscript as in the full nuclear symbol. So Ne20 or neon 20, and here's a table just comparing those three isotopes. They all have the same number of protons. The number of neutrons is what's different, and the mass number is the sum. 10 plus 10 is 20. Here's the natural abundance, and you see these numbers are somewhat random. They appear to be random. 90.48% is neon 20, 0.27% neon 21, 9.25% neon 22. Those are not numbers that we remember. If we need them, we look them up. Okay. So we should be able to answer questions like this. What are the atomic number, mass number, and symbol for the carbon isotope with 7 neutrons? Well, what's the atomic number for carbon? I have to find carbon on the periodic table. That's why I put one on here. What's the atomic number? 6. So atomic number is 6. That's Z. And that is the number of protons, right? And then it asks, what's the mass number? Well, the mass number is not listed on the periodic table. The periodic table does not give us direct information about the isotopes. The problem is telling us it has 7 protons. So the mass number A must be what? 6 plus 7. 6 protons plus 7 neutrons, or 13. Okay? And then the symbol. Well, there's a couple of different ways we could write the symbol. We could use the nuclear symbol. The element symbol is C, and the mass number up here, and the atomic number down there. Or we could call this C13 or carbon 13. 13, the mass number, is what we use to identify which isotope are we talking about. Here we're given a symbol for an isotope of potassium and asked how many protons and how many neutrons does it have? Well, the number of protons is easy. How many protons? 19. So 19 protons. So that is in the symbol, but if you don't remember, well, what was that 19? Maybe you think, maybe that's the neutrons, I don't remember. Find it on the periodic table. There's potassium. The 19 is right there in the periodic table. That tells me that's the number of protons. And then how do I find the number of neutrons? I subtract. So 39 minus 19 is 20. And it's all stacked up like that for you to do it without a calculator, but feel free to use a calculator. It's just dumb to get an answer like this wrong because you did mental math incorrectly. There is no shame in using a calculator. So 20 neutrons. Any questions? So what about the number of electrons? Well, atoms are neutral. They have no net electrical charge. And so the number of protons has to equal the number of electrons. There's a seat back there if you feel more for that. It's good too. So the number of protons is equal to the number of electrons. But in a chemical change, in a chemical reaction, atoms often gain or lose electrons. And then they become ions. An ion is a charged particle. So sodium can undergo a chemical reaction where it loses an electron. Now it has one more proton than electrons, and so it has a positive one charge. The charge is indicated as a superscript on the right side, and we always write the sign of the charge, and we write the magnitude if it's something other than 1. So we'll see throughout the semester there are a lot of places where chemists do not write the number 1. It's like we're lazy or something. I prefer to think of it as being efficient and concise, right? So here's an example of something gaining an electron, fluorine gaining an electron. Now it has an extra negative charge, and so overall it has a negative 1 charge. So that's F minus. I like to make up reasons for stuff because, it helps me remember. And so it really doesn't matter at all whether my reason is correct or not, because I'm not making it up for that purpose. I'm making it up to help me remember. So these signs, the charges, look a lot like, and they're in the same position as exponents in math, right? So in math, if you had x squared, you'd write x to the 2 power, and if you had x to the negative 2 power, you'd write x 2 minus, right? In math, exponents, if it's positive, you don't write the positive sign. With the charges on ions, we always write the sign. So calcium forms a positive 2 ion, and so it's calcium 2 plus. Okay, see, I'm such a chemist, I did this backwards. It's minus 2 in math. Just can't even help myself. Oxygen has a negative 2 charge, and so that's 2 minus. Because we don't want to confuse this for an exponent and think, there's O squared, or O to the negative 2 power. So we always put the sign after. That's another thing I'm not going to try to trick you on, but sometimes students wonder, well, why it seems backwards, I always keep getting it in there wrong. That's why it is. If the magnitude is 1, we just write the sign. Any questions? You should have seen this stuff before. Well, that was unexpected. I don't know what I did.